Okay, so we're going to continue in our modeling applications here. And so in the last section we just finished with our formal definition of what a system of first order differential equations looks like. Okay, and now we want to actually formulate a system of differential equations using two tanks as an example. And so in the two tanks, you might pause this and write down these numbers if you like. But I have incoming brine up here at the top, and it's 4 liters per minute at 6 grams of salt per liter. These numbers are really just arbitrary. And then 3 liters of water per minute is coming in this side, and in this case it's going to be fresh water. And then over here in tank B, I've got water leaving tank B at a rate of 7 liters per minute, and I've got some water being pumped from A to B at a rate of 6 liters per minute here, and from B to A at a rate of 2 liters per minute there. Okay, and both tanks I'm going to assume are 50 liters. And so one thing we might do before we look at the how to model the amount of salt in the tank at time t, this is salt here, is does the water level change in the tanks at all? So if you look, we've got 4 liters per minute coming into the tank A from the outside and 2 liters from tank B. So altogether for tank A we've got 6 liters per minute in and 6 liters per minute out. And so that's the amount of water in the tank in tank A will not change. And similarly in B, how many is coming in? We have 3 coming in from the outside, 6 liters coming in over from A. So that's 3 plus 6 is 9 liters per minute in. We've got 2 going out to A and then 7 out, just out. So 7 plus 2 would be 9 liters going out. Okay, and so the level in the tank B is not going to be changing either. Very good. So then, by the way, another way to check that is just to see, right, that altogether the amount going into the system from the outside is 7 for 4 and 3, and then what's leaving the system is 7. So 7 is coming into the system as a whole, and 7 is leaving as a whole. Good. Now, that kind of gives us a clue as to how we model this. Do you remember how to do that? So we'll go ahead and define our variables first. Let A of t and B of t be the grams of salt in tanks A and B respectively at time t. So t is being measured in minutes. Okay, and then the rate of change is going to be rate in minus rate out. So dA over dt equals rate in minus rate out. I don't know if I'm going to be able to include this with the picture. I'm going to try. Let's see, so for rate in, we've got 4 liters per minute from the outside, but then we also have 6 grams per liter of salt. And so notice here that this the units for the rate in is going to be grams per minute, and that is what we want, so the liters would cancel. Good. Plus we also have incoming from B, and so that's 2 liters per minute. And then what's coming in from B? We have B grams per 50 liters, right? And so that would also cancel the L's. Good. And then we subtract the rate out, and the rate out is just the 6 6 liters per minute, and that's times A grams in 50 liters. Good. So we could probably simplify that a little bit. Looks like 24 plus 2 over 50b minus 6 over 50a, and you could reduce those fractions if you like. Sometimes in the program it's easier to type it in if all the denominators are the same, so that's fine if you want to leave it that way. Similarly for dB over dt, let's see what's incoming. We have 3 liters per minute times 0 grams, so that would be 0 for that, for coming in from the outside. But then we also have the 6 liters per minute coming over, and so that was this quantity here, so that's 6 liters per minute times A grams per 50 liters. Good. And then we have minus what's going out, and that's you could put these together because they're both coming from the same source, really. You know, it wouldn't matter if you had this pipe here as shown, or you could put the pipe here. You know, it doesn't really matter where you put it, and then you could just add the two quantities together if you like. So you can just treat those as the same. So that's 9 liters per minute, and then that's going to be times the B grams per 50 liters. Good. And so again, now the liters cancel. All right. So then dB over dt, we get to be 6 over 50 times A minus 9 over 50 times B. And that's it. So now we have our system of differential equations. And so we could write this system as a in matrix form. So dA over dt, in fact, maybe I'll go ahead and say this is going to be a vector. So that'll be AB prime. Now remember, when I write this, I need to write this in terms of A and B, right? So I need to make sure my variables are lined up. Minus 6 over 50, 2 over 50. This is why sometimes it's easier just to write them with the same denominator, right? 6 over 50 minus 9 over 50. Good. And then this is with an A and a B. Okay, so that takes care of these 4 numbers. But then we have this constant of 24, and so I have this extra vector here, 24, 0. Good. All right. Now, just to let you know what's going on in the textbook, you'll remember that for these kinds of systems, this is called a, do you remember what it's called if the time does not show up in your differential equations? It's called an autonomous dE. Then we can find the equilibrium solution by setting the derivatives to 0, right? And so if I do that in this case, I get minus 6 over, maybe I'll take the 1 over 50 out here, and then this will be minus 6, 2, 6, minus 9, AB, plus 24, 0, equals 0, 0. Okay, and now we can solve that system of differential equations, right? That's just going to be minus 6, 2, 6 minus 9, AB equals, let's see, minus 24. Minus 24 times 50 will be 1200, so that's going to be minus 1200, 0. Oops, I'm getting this kind of sloppy there. And now this is just a 2x2 matrix. And let's see, I'll spare you the details, but what we get is that A is equal to 1800 over 7 and B is equal to 1200 over 7. And so these are the equilibrium solutions. What do they represent in terms of the initial model? Whoops, sorry about that. These are the values, or the grams of salt that are going to be in the tank for both A and B at time t. Over, it's the amount of salt that will never change. So once you get to this value closer and closer, the amount of salt will always stay that way. Okay, and so I'm going to pause here, and then in the next video we're going to see how to convert this system. You'll notice that right now we have something of the form x prime equals ax plus another vector b, and what I want to see is if I can convert this to something of the form x prime equals like a hat times x, because it's going to be important later on that we look at these types of differential equations. And so I'll pause here, and then we'll get to work on a little bit of algebra there. This is also being done in the homework as well, so I wanted to give you an example.